we're taking a true engineering deep dive into the EinScan Medixa from Shining 3D. We're going to examine the optical architecture, triangulation mechanics, tracking algorithms, error sources, mesh generation, and product integration. So if you're evaluating scanning systems for clinical manufacturing, prosthetics, or medical R&D, congratulations, you found your people. Hello chat, I'm Steven here with UMax. Let's dive right in. At the hardware level, the Mediaxa operates using structured white light triangulation. It combines a pattern light projector with dual stereo cameras mounted at a fixed baseline and synchronized for real-time frame capture. What's happening here is the projector emits a known spatial pattern across the surface. The two cameras observe how that pattern deforms in 3 dimensions. Using disparity mapping between the camera pair, the system calculates depth through triangulation. In simpler terms, every pixel becomes a ray in space, and depth is calculated by measuring angular separation between the cameras. But yes, it's basically doing trigonometry at thousands of points per frame. Somewhere a math teacher just felt appreciated. Because this is structured light instead of laser, we get faster acquisition, reduced speckle noise, safer operation around patients, and much better performance on soft tissue. The system is optimized specifically for short range, high detail anatomical scanning, not for scanning your garage, your dog, or your coffee mug, although I know you're tempted. Each captured frame produces a high density point cloud with sub-millimeter geometric resolution. Unlike line-based laser scanning, this is full field acquisition, meaning the entire surface is captured at once. Resolution settings directly affect point spacing, polygon density, reconstruction fidelity, and overall processing load. From an engineering perspective, higher resolution improves edge definition, but it also increases VRAM usage, meshing time, and CAD overhead. So yes, more resolution is great until your workstation sounds like it's preparing for liftoff. For most prosthetic workflows, medium resolution is sufficient for macro geometry. High resolution should be reserved for socket interfaces, joint articulation zones, or areas requiring tight anatomical conformity. The MediaXA uses geometry-based tracking with no physical markers. Each new frame is aligned against the cumulative mesh using curvature matching and ICP style registration. The system looks for persistent surface features across frames to maintain alignment. Common tracking failure points include low feature surfaces, rapid angular movement, insufficient overlap, and repetitive geometry. In other words, if you spin the scanner like you're DJing at a nightclub, tracking will fail. Ask me how I know. Best practice is maintaining 30 to 50% overlap between passes, keeping scan distance consistent, and avoiding sudden orientation changes. After acquisition, global optimization recalculates alignment across the entire dataset, reducing cumulative drift. Always run global alignment before exporting. Think of it as letting the scanner think about its life choices before committing to the mesh. The primary sources of accuracy degradation are thermal drift, improper calibration, surface reflectivity, motion distortion, and exposure imbalance. Calibration aligns projector geometry, camera orientation, and baseline compensation. From an engineering standpoint, recalibration should be performed after transport, environmental changes, or extended runtime. Ambient lighting should remain diffuse and consistent. Reflective surfaces may require matte spray when clinically appropriate. Best accuracy is achieved when the scanner remains perpendicular to surface normals, working distance stays consistent, and motion is slow and controlled. Think of it as metrology-grade acquisition, not photography. The scanner does not care about your angles. Internally, the system processes data through a structured pipeline. First comes frame alignment, then point fusion, followed by surface reconstruction, noise filtering, hole detection, and finally watertight mesh output. This likely uses volumetric fusion or implicit surface modeling for stability. Over-aggressive smoothing reduces dimensional fidelity. Automatic hole filling can fabricate geometry that was never captured, which is great for video games, not great for medical devices. For production critical workflows, missing data should be rescanned rather than artificially reconstructed. Typical export formats include STL for additive manufacturing, OBJ for texture workflows, and PLY for point cloud analysis. Before importing into CAD, always verify scale integrity, unit consistency, water tightness, and edge continuity. To maintain CAD performance, recommended triangle counts are roughly 300 to 800,000 faces for full body scans and 150 to 400,000 for localized anatomy. More triangles do not make you more professional, they just make your CAD software sad. A typical engineering grade workflow looks like this. Calibrate the system, capture with consistent overlap, run global optimization, remove noise artifacts, validate dimensional accuracy, optimize mesh density, export to CAD, apply design modifications, then manufacture using additive or subtractive processes. Skipping steps in this pipeline is how prototypes become learning experiences. Compared to laser-based systems, structured light offers faster full field capture, better soft tissue compatibility, and lower operator training requirements. Compared to photogrammetry, it provides immediate reconstruction, controlled geometry capture, and far less post-processing. For medical surface acquisition and prosthetic workflows, this places the Medixa in a strong position for controlled, repeatable digital manufacturing. This concludes our engineering deep dive into the EinScan Medixa. If you're evaluating this system for clinical production, R&D, or digital manufacturing pipelines, I hope this breakdown helped clarify how it performs beyond the marketing specs. Or if you'd like a tolerance analysis, repeatability benchmarking, or a comparison against our laser systems, let me know below in the comments. Now, if you're looking for your own 3D scanner, software, accessories, or you'd like to schedule a free demo to understand how 3D scanning can improve your workflow, visit us at umax.com for all your scanning needs. This is Steven from UMax. Thanks for watching, and I'll see you in the next one.